Hello everybody, welcome back to Math 251. I hope you're having a great day. Something that you ought to know about me is that I have a dog. She is beautiful and perfect in every single way. Her name is Athena and she is a German Shepherd Lab mix. She's 4 years old, and when I teach classes in person, I often show my students videos and pictures of Athena because she's the cutest dog in the world, and I think everybody deserves to see pictures and videos of her. So anyway, all of this to say that I will be sending you guys periodic pictures and videos of Athena because she is adorable and I think that you ought to see her. Yeah, she's amazing. So anyway, if you're ever needing a pick-me-up, just email me and I can send you a picture of her. Our mathematician of the day today is Emmy Noether. She was a German mathematician born in 1882 who made such important contributions to a field known as abstract algebra that Einstein called her the most important woman in mathematical history, which is a pretty darn big deal. So she was amazing. And did you know that Chinese mathematics developed around 1100 BC and included important concepts such as negative numbers, decimals, and algebra? In other parts of Europe, when negative numbers were first developed, after they developed in China, a lot of mathematicians were shunned from mathematics communities because of their belief in negative numbers, but the Chinese people obviously did not believe this, so they were pretty far ahead in math, seeing as how this math developed around 1100 BC. So pretty cool. All right, like I said, today we will be focusing more on how to find limits, and we are starting with a theorem. This is the limits of linear functions. So we have a, b, and m, they're real numbers, and if I have a linear function, f of x equals mx plus b, then the limit as x approaches a of f of x is simply this function evaluated at a. So this is f of a is equal to ma plus b. So what this is saying is that if I am trying to take the limit of a linear function, I can just plug in my point x equals a into my function in order to solve for the limit. I can plug in x equals a to my function. This is true because linear functions don't have any discontinuities, they don't have any strange jumps, so in order to find a limit, we can simply plug in a point. And actually, we'll be talking about another version of this theorem later on today. We also have some other rules that can help us compute the limits of various functions. These are a lot of rules, so don't get overwhelmed. We will be doing lots of practice today using all of these different rules. So I first assume that two limits exist. I assume that the limit as x goes to a of f of x and the limit as x goes to a of g of x. I assume that these both exist. Then the following properties hold, where c is a real number, it's just a constant, and n is greater than 0 is an integer. Our first rule is called the sum rule. This says the limit as x approaches a of f of x plus g of x is equal to the sum of the independent limits. So I take the limit as x goes to a of f of x plus the limit as x goes to a of g of x. So this is saying the limit of the sums is equal to the sum of the limits, is what this rule is. Similarly, we have a difference rule, which is basically the same thing. It says the limit as x goes to a of f of x minus g of x is equal to the limit as x goes to a of f of x minus the limit as x goes to a of g of x. So these sum and difference rules can help us find lots of limits if we just combine functions in this way. This does not stop with two functions either. If I were to take the limit as x goes to a of f of x plus g of x plus h of x, I could split those up into 3 parts as well. It doesn't just have to be with 2. Our next rule is called the constant multiple rule, and it says the limit as x goes to a of c times f of x. So if I have a constant times a certain function and I'm trying to take the limit of it, I can bring this constant out in front and I can say this is c times the limit as x goes to a of f of x. So I can basically factor out that c and put it in front of the limit. That is known as the constant multiple rule. Next up, we have the product rule, which says the limit as x goes to a of f of x times g of x is equal to the product of their limits. So I can simply take the limit as x goes to a of f of x and multiply this by the limit as x goes to a of g of x. So if I have two functions that are being multiplied together, I can simply take the limits of the individual functions and multiply those limits together. All right. Now we have the quotient rule. This says the limit as x goes to a of f of x divided by g of x. Hopefully you sort of have a guess as to what this is. This is the limit as x goes to a of f of x divided by the limit as x goes to a of g of x, as long as the bottom limit is not equal to 0. So as long as the limit as x goes to a of g of x is not equal to 0, because we can't divide by 0. That is undefined. We have the power rule, which says the limit as x goes to a of f of x to the power of n. So if I have a function raised to a power, this is equal to the limit as x goes to a of f of x, the limit raised to the power of n. So we can raise a limit to a power instead of raising the function to a power. Our last rule is known as the root rule, and it says the limit as x goes to a of f of x to the power of 1 over n, so this is the nth root, is equal to the limit as x goes to a of f of x. We can take the nth root of the limit, provided that this limit is positive if n is even. Since we can't take the positive root of a negative number. Whew, so that's a lot of rules, but like I said, we'll be doing lots of practice today in order to practice these rules in order to understand how to use them. So let's go ahead and do an example. I want to suppose the following. Say I have a function, actually multiple functions, that have the following limits. So I have the limit as x goes to 1 of f of x equals 4. I have the limit as x goes to 1 of g of x equals negative 2. And the limit as x goes to 1 of h of x equals 6. So I have these three functions, and I have the limits of each of them as x approaches 1. And I want to use the rules that we just learned in order to compute the following limits. So let's first compute the limit as x goes to 1 of f of x minus g of x over h of x. So we are combining a couple rules that we just learned here, but that's okay because we can use more than one rule at once. So on the top here, I have two functions that are being subtracted from each other. So we're going to have to use the difference rule. That's rule number 2. And then because I have a quotient, I'm also going to use the quotient rule, or rule number 5. So we can rewrite this as the limit as x goes to 1 of f of x minus the limit as x goes to 1 of g of x. That's on the top, right? Because I'm taking the limit as x goes to 1 of two things subtracted from each other. So I can plug each of them into their limits and just subtract their limits from each other. And then over this, I have divided by the limit as x goes to 1 of h of x. So this was rules 2, the difference rule, and 5. All right, and now I can simply plug in what each of these are. So I know that the limit as x goes to 1 of f of x, it was given to me. I know that this is equal to 4. Minus the limit as x goes to 1 of g of x, which was given to me as negative 2, over the limit as x goes to 1 of h of x, which is 6. So I have 4 plus 2 over 6, which is just equal to 1. So the limit as x goes to 1 of f of x minus g of x over h of x is just equal to 1. We combine lots of different rules here, rules 2 and 5, the difference rule and the quotient rule. Our next example looks like this. We have the limit as x goes to 1 of 6 times f of x g of x plus h of x. So you are going to be using the sum rule since we are adding two things, the constant multiple rule since I have that 6 in front of the f times g, and the product rule. So this involves rules number 1, 3, and 4 above. I would like for you to pause this video and try this example by yourself using these rules 1, 3, and 4. So pause it and give it a try on your own. All right, hopefully you have paused the video and have tried this on your own. So like I said, we are going to be using these 3 rules. So let's first use the constant multiple rule. So if I were to divide this into several parts, I could rewrite this as the limit as x goes to 1 of 6 times f of x times g of x. I'm just splitting it up into 2 parts for now. And then by the sum rule, I can split this up to say the limit as x goes to 1 of h of x. Now, using the constant multiple rule, I can bring this 6 out in front. So this will be 6 times the limit as x goes to 1 of f of x times g of x plus the limit as x goes to 1 of h of x. So the first thing we did here in our first line was that we used rule number 1, the sum rule. Then I used the constant multiple rule in the second line. So that is rule number 3. Now, since I have that f of x times g of x, I am going to be using the product rule. So I have 6 times the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x plus the limit as x goes to 1 of h of x. This was the product rule, rule number 4. And now I can combine all of these. I know that I have 6 times the limit as x goes to 1 of f of x is equal to 4. The limit as x goes to 1 of g of x is negative 2. Plus the limit as x goes to 1 of h of x is equal to 6. So I get negative 48 plus 6, which is negative 42. That is our answer here. So again, we combine 3 rules of the theorem above in order to solve this limit. So hopefully you're kind of getting the hang of using these rules now. And our last example uses a different one of the rules. We want to find the limit as x goes to 1 of g of x to the power of 3. G of x cubed. Now I don't know what g of x looks like, so I definitely don't know what g of x cubed looks like, but I have the power rule, rule number 6, that I can use in order to solve this. So by rule number 6, I can write this equals the limit raised to the power of 3. So the limit as x goes to 1 of g of x, the limit raised to the power of 3. Well, I know that the limit as x goes to 1 of g of x is equal to negative 2. So this is negative 2 to the power of 3, which is just negative 8. So even though I have no idea what g of x looks like or what g of x cubed looks like, I can still use these limit rules in order to find this limit. All right. Next, we have another theorem that is kind of an add-on of the very first theorem we learned today, the linear function theorem. So the next theorem that we are going to be learning is called the polynomial function theorem. So I assume that p and q are polynomials and that a is a constant. My first rule says that the limit as x goes to a of p of x, this is just a polynomial, so the limit as x goes to a of some polynomial is simply that function evaluated at a. Again, this is because polynomials don't have any sort of discontinuity, they don't have any sort of jumps or anything, so the limit of this function is simply the function evaluated at this limit. So I can plug in x equals a to find my limit. The second rule is called the rational function rule, and it says the following: the limit as x goes to a of p of x over q of x is equal to p of a over q of a as long as q of a is not equal to 0. Since we can't divide by 0. So these rules are super helpful as well because it allows us to take the limit pretty easily of polynomials and rational functions as long as the denominator of the rational function is non-zero. So let's do an example with these two theorems now. I want to evaluate the following limit. I want to evaluate the limit as x goes to 2 of x cubed oh, sorry, x squared, minus 3x over 3x cubed plus 6. Now, if I were to plug in x equals 2 into the denominator, it does not equal 0. So, according to my polynomial and rational function rules, I can simply plug in x equals 2. So, since the denominator does not equal 2, does not equal 0 when x equals 2, I can simply plug in x equals 2. So this will be 2 squared minus 3 times 2 over 3 times 2 cubed plus 6, which will give me 4 minus 6, or negative 2, over 2 cubed is 8, times 3 is 24, plus 6 is 30. So negative 1 over 15 is this limit. So this used the rational function rule. As long as the denominator is not equal to 0, the limit of a rational function is simply the function evaluated at that number. So pretty straightforward here. So last time we talked about this notion of one-sided limits, so the limit as x approaches a number from the right and from the left, and how those are different from each other. So these rules that we learned up here, rules 1 through 7, these hold when we are dealing with one-sided limits, except for law number 7. Law number 7 was the root rule. So all of the other rules stay the same when we're dealing with one-sided limits, except for number 7, which is modified like this. So the limit as x approaches a from the right of f of x raised to the power of 1 over n, this is the root rule, is equal to the limit as x approaches a from the right of f of x, all of this raised to the power of 1 over n, provided that if n is even, f of x is greater than or equal to 0 for x near a when x is greater than a. So all this is saying is that we have to be careful when we are dealing with the root law in one-sided limits, because our number has to be even, it has to be positive on the inside if I'm taking an even root, since I can't take the even root of a negative number. That's all this is saying, that the limit has to be positive if we're taking an even root. The same thing is true for the left-sided limit. So if I have the limit as x approaches a from the left of f of x to the power of 1 over n, this is equal to the limit as x approaches a from the left of f of x to the power of 1 over n. And again, we still need the inside to be positive if n is an even root. So provided that if n is even, f of x is greater than or equal to 0 for x near a when x is less than a. These are pretty obscure rules, so I wouldn't worry too much about memorizing these rules, though you may have to use them on something like your online or written homework. But they are pretty obscure, so just so you know. All right, next we have an example. So we want to find the limit of a piecewise function. So I let f of x equal the following function. Negative 3x plus 6 if x is less than or equal to 0. And the other piece is the square root of x plus 1 if x is greater than 0. So I want to find the limit as x goes to 0 from the left of f of x, the limit as x goes to 0 from the right of f of x, and the limit as x goes to 0 in general of f of x. So I want to find these or state that they do not exist. Hold on 1 second. Sorry about that. Okay, so I want to find these limits or state that they do not exist. All right, so let's first draw this piecewise function because it's kind of unclear what it looks like just by looking at it. So I have a graph, and if x is less than or equal to 0, then my graph is negative 3x plus 6. So this line has a y-intercept of 6. Has a y-intercept of 6 and a slope of negative 3. So this graph looks something like this when x is less than or equal to 0. And then when x is greater than 0, we have the square root of x plus 1, which has a y-intercept of 1. I have an open circle there since I cannot equal 0. And I look something like this. So I do have a jump discontinuity here, but this is what my function looks like. So if I find these limits now, I want to find the limit as x goes to 0 from the left of f of x. So if I'm going to 0 from the left, I'm going to be on this linear piece right here. And as I approach 0 from the left, I am approaching the point 0, 6. So my y value here is 6. If I approach 0 from the right, the limit as x goes to 0 from the right of f of x, that's going to be on this piece right here, the square root piece. And even though I'm not defined at 0, kind of like we talked about last time, I still have a limit. So here I'm approaching the point 0, 1, so my y value is 1. However, we see that the right-sided limit and the left-sided limit do not agree with each other. So we have to use that theorem we talked about last time, saying that the limit in general only exists if the left and the right-sided limits are the same number. So the limit as x goes to 0 in general of f of x does not exist, D, N, E, since the right-sided limit and the left-sided limit are not the same number. All right, next we have another example that we're going to have to pull out some tricks for. So we want to evaluate the limit as x goes to 0 of x squared minus 6x plus 8 over x squared minus 4. Oops, sorry, this should be the limit as x goes to 2. Limit as x goes to 2 of x squared minus 6x plus 8 over x squared minus 4. So we had that rational rule that said that if I have a rational function, then I can simply plug in my limit point as long as the denominator is not equal to 0. Unfortunately, here, when I plug in x equals 2 into the denominator, I get 0. So my denominator is equal to 0, so I can't use direct substitution. else could I do here? Well, let's try to factor the top and the bottom to see if anything cancels out. So the top is going to factor as limit as x goes to 2. The top factors as x minus 4 times x minus 2, and the bottom factors as x plus 2, x minus 2. Well, hey, check it out. The x minus 2 on the top and the bottom cancel out with each other. And now, when I plug in x equals 2 into the bottom, my denominator is not equal to 0. So now, the denominator does not equal 0, so I can plug in. So I plug in x equals 2 to the bottom and the top, since my denominator no longer equals 0. This will be 2 minus 4 on the top, 2 plus 2 on the bottom, which is negative 2 over 4, also known as negative 1/2. So this is the limit of the original function, even though I canceled some stuff out. So this is the limit as x goes to 2 of x squared minus 6x plus 8 over x squared minus 4. The limit of the original function, even though we canceled some stuff out. All right, we have one last tool that we need in order to compute limits. This is known as the squeeze theorem. This is a little bit tricky, so I would pay extra close attention to this rule. So here is the squeeze theorem. I assume that the functions f, g, and h satisfy the following inequality. F of x is less than or equal to g of x is less than or equal to h of x for all values of x near a, except possibly at the point a. Then, if I have the following, if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, so this first function here and the last function here, if these two are the same and they equal a number called L, a constant, then the limit as x goes to a of g of x also equals this number. Because it's essentially being sandwiched or squeezed between the upper function h and the lower function g. So here's what this looks like. Let's do an example. I want to use the squeeze theorem to verify that the limit as x goes to 0 of x squared times sine 1 over x is equal to 0. This is kind of a weird function. If you were to graph this function, it would be pretty wacky. But luckily, we have the squeeze theorem to help us here. So let's first just look at the function sine of x. My goal here, using the squeeze theorem, is to sandwich my function above and below by a certain number, or two functions that evaluate pretty easily. So I'm going to look at sine x first. So if I think about the function sine of x is bounded above by the number 1, right? Sine of x cannot be greater than 1. And it's bounded below by negative 1. So I know that the function sine of x is sandwiched between negative 1 and positive 1. Well, this makes it true of sine of 1 over x. The only thing that changes when I put 1 over x inside the sine is the period is changing. So sine of 1 over x is also bounded above and below by negative 1. So that is this piece right here. And then in order to get my function that I'm trying to find the limit of, I just have to multiply this function by x squared. So next I'm going to multiply everything by x squared. So this will give me negative x squared over here is less than or equal to x squared sine of 1 over x is less than or equal to positive x squared. So now, what does this look like? Well, if I were to graph negative x squared and positive x squared, they just look like positive x squared, negative x squared. So my function x squared sine of 1 over x is sandwiched between these two functions. So this function looks something like this. Pretty weird. And the squeeze theorem tells me that the limit, since I am bounded above and below by x squared and negative x squared, the limit as x goes to 0 of x squared sine of 1 over x is equal to the limit as x goes to 0 of either negative x squared or positive x squared. Well, I know that this is just equal to 0, right? So I was able to use this fact because I know that the limit as x goes to 0 of our lower function here, negative x squared, was equal to 0. And 0 also equals the limit as x goes to 0 of our upper function here. That's why I was able to use the squeeze theorem. So basically the squeeze theorem tells me that if I have two functions that are sandwiching another function inside that's bounded above and below, then I can take the limit of this sandwich function as long as the limits of the outer two functions are the same. In this case, the limits were the same. The limit as x goes to 0 of negative x squared is equal to 0. And the limit as x goes to 0 of x squared is equal to 0, which meant that the sandwich function, x squared times sine of 1 over x, was also equal to 0 at the point 0. So in general, if I wanted to use the squeeze theorem, it would look something like this. Now let's do it in red. So I have maybe a function down here. That's my lower function, f of x. And then maybe I have a function here. Let's draw better than that. And then I have an upper function, maybe like something like this. So this upper function is my h of x. This middle function is my g of x. And this lower function is my f of x. So they could be super weird, just like this. But as long as they are the same, right, the limit as x goes to a of f of x and h of x are the same, then I know that that is also the limit as x goes to a of g of x. So this is what the squeeze theorem looks like in general. It is handy, especially when we're dealing with trigonometric functions. Yeah, it can be tricky, but hopefully you can do some more examples on your online homework as well. All right, that's it for today. As always, let me know if you have any questions, and I will see you next week. Have a wonderful weekend.